Let's take a look at this one real quick. Let's use the shell method to find the volume of the solid that's formed by revolving the region that's bounded by this function, 2x plus 1, and y equals 0. Of course, y equals 0, that's the x-axis. And we're going to revolve that region about the y-axis over the interval from 0 to 2. Okay, so what's happening here? So I'm going to graph the function. F of x is just a linear function. Y-intercept is 1, slope is 2. And on the interval from 0 to 2. So at, of course, f of 2 is equal to 5, right? And so that's the height there. And so shaded in this region, this is the region we're going to rotate about the y-axis. So we're rotating this way. So it's going to come out of the page, rotate back into the page. So on the outer side of it, it looks like a cylinder. If we look at it from the top, there's a funnel shape inside here, but we're looking at the volume of the solid object that we've constructed by rotating or revolving this region about the y-axis. So what I'm going to do is integrate with respect to x, right? So at an arbitrary distance from the y-axis to this arbitrary rectangle, I'll call that distance x, right? X is going to vary from x equals 0, which is the y-axis, to x equal 2, right? That's on this interval from 0 to 2. And this rectangle, as I rotate that about the y-axis, it's going to form thin cylindrical shell, right? A thin cylindrical shell. So that rectangle will rotate around, go back into the page, right? Come behind the page, come back in, back into the front of the page and around, forming this shell. So it's rotating about the y-axis. And for the shell, what we talk about is the radius of this circle. I'm going to call that P of x. It's a function of x. And the height of this shell, I'm going to call h of x. Now, to find the area that we're talking about here, take some scissors and cut open this cylinder and unroll it, right? And what we'll have is a rectangle. The height will become the height of our rectangle. And what's this width going to be? What's the distance around a circle, which is the pi times the diameter, or pi times twice the radius. Since the radius is P of x, it's 2 pi times P of x. That's the circumference really around the circle, is that length. So the area of our shell is the length, 2 pi P of x, times the height, h of x. Of course, there is some thickness to the shell. It's really a slab. So we have a dx, right, which will become or a delta x, which will become our dx. But we're just going to integrate this cross-sectional area. Right. Now, what is P of x and h of x in this particular problem? Well, the distance from the y-axis to the rectangle, from the y-axis to the rectangle, that's x. So P of x is just x. And the height of this rectangle is the height is going to be the h of x. And that's going from y equal 2x plus 1 to y equals 0. So the h of x is 2x plus 1. So to set up the problem, then we're just going to integrate the cross-sectional area here. 2 pi P of x, h of x, 2 pi will come out, integrating, of course, from 0 to 2. P of x is x, and h of x is 2x plus 1. And this is pretty easy to then evaluate the integral. First, make sure you simplify by distributing the x through here. I get 2x squared plus x. Antiderivative of 2x squared is 2/3 x cubed. Antiderivative of x is 1/2 x squared. Evaluate it at 2 and at 0 and subtract. We get this expression and gives us 44 pi over 3. So there's the evaluation of that. Now, I just want to do a little variation of this real quick. What would it look like if instead of rotating this region about the y-axis, we rotated it about the line x equal -1? Okay, well, what would that look like? Well, if I rotate about the line x equal -1, so of course the y-axis right here, that's x equals 0, right? Vertical line x equals 0. Here's the line x equal -1. So if we rotate it around there, now we're going to come out, right? Go back into the page. We're going to have the outside of a cylinder, but in the middle, we're going to have a sort of a cylinder drilled out of it, right? There's going to be a sort of drilled out cylinder. So if I rotate this thing, I don't know, let me try and see if I can draw this shape on the outside. It does look like a cylinder. But then there is a hole in this cylinder. I'm terrible at drawing these things, but there's a hole here. And also there's this, you know, funnel shape, right? From these edges, there's a funnel shape going down. Maybe not quite to the bottom there, sorry. Okay, there's a hole in it. Sorry, terrible drawing. But the volume of the solid now, how's that going to vary? Well, this rectangle, here's my arbitrary rectangle, distance x, right, from the y-axis. It's going to rotate now along this line, so it's going to come all the way over, right, and form that thin shell. So notice our p of x is this distance, right? It's that distance. So what is that distance? Well, essentially, you can see from -1 to 0, that's 1 unit. This is x, so it's x plus 1. Or you can think this is at, you know, x equal x, and this is x equal -1, so x minus a -1 is x plus 1. So notice that the p of x changes. The h of x is the height of our rectangle. That does not change. That's the same as it was previously. And so the integral now looks like this. So instead of x here, we've got x plus 1. Again, I'm not going to evaluate this, but we could, you know, FOIL that out and evaluate that integral. Okay, so that's an example of how to do the shell method. And I hope that this will help.